Hello, everyone. I'm Bernard Murphy, your moderator for today's SiFive Connect webinar. I'm an author, blogger, advisor on systems, SoC, and IP, and I blog regularly at semiwiki.com. I previously worked in R&D, marketing, and sales in semiconductor and EDA companies. This webinar is titled Rapid Embedded Prototyping with SiFive Software. In this webinar, you will learn how to develop embedded software for RISC-V processors using the SiFive Freedom E SDK. There are two speakers, Sam Grove and Bunaroth Su. Sam Grove is the Director of Product Management for Software at SiFive. He has 15 years of experience in embedded software, operating systems, and community-driven open source software development. Prior to joining SiFive, he worked at ARM for over 6 years in various software architecture, applications, and engineering management positions. Sam earned his BS degree in electrical and electronics engineering at California State University, Long Beach. Sam will introduce SiFive's Freedom tools and SDK, and will discuss details of Freedom E SDK for embedded programming. With nearly 3 decades of experience in engineering, Bunaroth serves as engineering manager of RISC-V tools at SiFive. Prior to joining SiFive, he was a principal engineer at Juniper Networks for over 8 years. Before that, he was a technical leader at Cisco for almost 10 years. Bunaroth earned his BE degree in computer engineering at the University of Newcastle. Bunaroth will demo to us how to build and run embedded RISC-V software using Freedom E SDK. Quick note on logistics, please submit your questions as the webinar proceeds, and they will be answered at the end. Now, over to you, Sam.
Thanks for the introduction. As mentioned, we're going to spend the next 20 minutes getting an overview of the SiFive software offerings, look a bit deeper into the Freedom E SDK, and run through a demo to introduce just how easy it is to get started writing software for RISC-V. Now, before we start diving into the Freedom E SDK, a little bit of background about SiFive. SiFive's mission is to make custom silicon available to everyone. To make this happen, we develop and license highly configurable RISC-V core IP. These are the processors that we're going to be learning how to write software for today. SiFive also builds and licenses other bits of IP to build out SoCs that are specific and targeted to the end application's needs. Because of the clean sheet approach taken with the RISC-V architecture, the design team also got to consider security from the beginning. When it comes to realizing your ideas in silicon, SiFive has deep expertise in reviewing specs all the way through the design process and into production. Of course, none of this would be possible without close collaboration with an ecosystem. The specification for the RISC-V ISA is managed by the RISC-V Foundation. There we collaborate on extensions and moving the specification forward with dozens of other companies, making sure that RISC-V is suitable for everyone. While there is more openness around RISC-V than any other ISA, there is also a huge amount of support from the commercial tools and software industry to ensure the best of the best is available when building with RISC-V. You can find out more on SiFive.com. In future webinars, we can go deeper into other SiFive software and tool solutions. But for today, I just wanted to present them to create awareness to the other areas that SiFive invests in the software space. For early silicon bring-up, all the way to embedded software development, we have an Eclipse-based development environment called Freedom Studio. This packages all the software pieces and brings them together into a unified environment. This includes support for SiFive Insight, our debug and trace solution. This, combined with a toolchain, debugger, and emulator, plus the Freedom E SDK, Freedom Studio truly pulls everything together. We also build and release the toolchain, debugger, emulator, and some utility programs for Windows, Mac, and Linux to use standalone. The scripts and patches, if any, for these tools are found on GitHub in the Freedom Tools repository. You can also download the pre-built executables from our website. I might have mentioned this earlier, but the SiFive RISC-V Core IP offering ranges from small single-issue 2 to 3 stage pipeline cores typically found in microcontrollers or subsystems, all the way up to dual-issue 8-stage superscalar pipeline application processors running Linux. Software support for the application cores running Linux comes from the Freedom E SDK. Based on Yocto, this allows you to layer your dependencies and create your own embedded Linux distribution. There are rootfs images attached to each release for our development boards, or you can check out and build the software yourself and extend it based on your needs. Finally, what today's webinar is all about is Freedom E SDK. So as you can see, there's quite a comprehensive effort put forth by SiFive, delivering what you would expect, plus a little bit more of an IP company or a silicon company. From a development perspective, we put effort into ensuring that there are silicon development boards, FPGA development boards, and emulators available to support you all throughout the silicon design process. The flexibility in prototyping platforms allows for software and hardware teams to work alongside each other and to find hotspots or areas for improvements much earlier in the design cycle, ultimately leading to better end silicon when working with SiFive. The demo today will be downloading a SiFive standard core. This means it's already been configured, and we'll develop for it on an easily available FPGA board. And as mentioned before, the embedded software ecosystem for RISC-V and specifically SiFive silicon on Core IP has most of the biggest names from the industry. This is true both for the open source and commercial side of the industry. We have or do work closely with these key players, plus many, many more, to make sure that the best solutions are available for SiFive products. Okay, so let's now start to dig further into the Freedom E SDK. In a sentence, the Freedom E SDK is an embedded software development kit providing a command line driven workflow for SiFive RISC-V development boards and Core IP. It pulls together quite a few things. There are example programs that will explain how to get started or how to use a particular feature of the development board or the CPU. We're adding more all the time, refining them and simplifying them where possible. As far as board support goes, you can target a silicon development board like the Hi5 One. Today, we'll demo on an FPGA development board. There is also support for running the software in RTL simulation or under the QEMU emulator. In a silicon design cycle, benchmarks are important to see how your design is performing and how you are improving or regressing the design. Of the examples, CoreMark and Drystone benchmarks are provided, so you can quickly and easily evaluate your design and compare it to something in silicon, and then model how it might end up. Finally, I mentioned how configurable the SiFive RISC-V core IP is. This might sound like a nightmare for software, but that is where the Freedom E SDK really shines. The board support is generated by some design metadata. More about that in a few slides. But the Metal library provides a portable programming interface across all these configurations. It's really slick. There are two ways to get the Freedom E SDK. Today we'll be logging into SiFive Core Designer, an online design tool, and downloading a standard core. This comes with a pre-configured version of the Freedom E SDK for that specific core. If you had a SiFive 1 board, for example, you could head over to GitHub and clone the repository. Looking into the structure of the Freedom E SDK, there are a few directories of importance. The BSP directory, which has the device-specific files, the linker scripts, etc. Then there's the software directory, which has all the example programs. And again, we're adding more and refining them with each release. And finally, the Freedom Metal directory. And this essentially is the API for writing portable software for RISC-V core IP. Now, the BSP directory may look a bit different if you clone from GitHub. And I say cloned because there are a lot of submodules, so downloading a zip from GitHub doesn't expand everything that you need. Versus when you download the IP delivery from SiFive Core Designer. Downloading from SiFive Core Designer, this will be a trimmed and focused deliverable specifically for the core that you designed or selected. To explain a bit more how the board support works and why the configurability of the cores isn't a problem, let's take a walk through how we do this. As part of the SiFive design methodology, there is a design metadata file that is provided in device tree format. This describes what is in the design, how big it is, and where it is placed, for example. We can take this file and run it through a tool naturally named Device Tree Tools, and it will transform the design metadata into header files, linker scripts, and some settings files for make and OpenNoCD. Looking at the files it generates, settings.mk has the arch type and ABI type for the toolchain to make sure you build and link with the best options possible for the design. Metal.h is a header file and is used by the Metal library. Once a single file that can get very large for complicated designs, it's now a few files that are logically separated. Metal platform has the memory mapped peripheral macros and definitions, and Metal inline has the function prototypes for small, low-level access to the specifics of the design. There are a few linker files created as well for running from different memory locations. Some development boards have QSPI flash, and other times you might want to tune a function or algorithm running directly from RAM to get the best performance, say benchmarks, for example. Now that we understand what's in the Freedom E SDK, how it handles the complexity of configurable cores, let's have a look through the command line interface it provides when you develop using it. First things first, there are some dependencies for the development machine. Things like git and make are generally available. On the SiFive website, you can download the pre-built toolchain and QEMU emulator for Windows, Mac, or Linux. Finally, some boards have the Segur JLink OB on them. You can download the Segur tools from the Segur website for Windows, Mac, or Linux. You can test your system, in this case, Mac or Linux, using the which command or where on Windows to make sure these tools are installed and exposed properly in your system path. You can see on my system that JLink is not properly configured, but that's okay for what we're doing today. This is a command line driven interface based on make and make files, so it's easily understandable or Googleable. There's nothing bespoke that you need to learn about the tools or build process in order to develop your software. There are commands you'd expect like clean. This will delete the compiled objects for a program, target, or configuration. Speaking of configurations, there are two defined configurations, debug and release. Debug makes sure that you can step through your code and understand how the instructions executed relate to the source code by lowering optimizations. Release, on the other hand, will produce much smaller and faster code. If you want to build an example program, Make Software will build the program for the specified target and configuration. Once this is built, you could enter something like make upload, and that would flash it to the board that you are developing with. When the program is running, make debug will attach the GDB debugger to a running target. A little tip here, make sure that the program on the target is what you think it is. That is, that you have built and uploaded your program to that board. You have the flexibility to debug a release configuration, but that may or may not be useful. For best results, building and uploading a debug configuration will give the best human readable experience in the debug environment. If you do not have a board, you could simply run the program under a simulation or emulation environment. If you build for the QEMU target, you can run it in the emulator simply by entering make simulate. This next one is really useful when working in teams. If you need to pass off your files to someone else for help, you can shrink wrap the specific program and environment with make standalone. This will copy all the files for your program and board support target and move them into a single directory that can then be zipped up and shared. Assuming the tools are the same on multiple people's machines, this gets you a nearly reproducible development environment with almost no effort. And finally, when deep in the process of writing software applications, if you need to reference the docs, make open docs will launch your default browser and load the local version of the docs. This means you can develop offline without an internet connection and not lose a beat. Super handy in strictly controlled corporate environments too. So the Meta library provides hardware abstractions so you can write portable software for SiFive RISC-V Core IP. It also handles a bit more than that. It takes care of the startup of the CPU and the SoC subsystem, as well as initializing the standard C library. There are two files of concern with regards to startup. Entry.s, which configures the global pointer, handles the stack pointer initialization, and then passes off to _start and crt0.s. Then libgloss retargets all the syscalls, and crt0.s handles the RAM init, relocatable code setup, and the floating point checks, all before calling main. As for the hardware abstractions, it provides there are abstractions for RISC-V Core IP to twiddle things in the CPU using CSRs and the like, as well as register interrupts, control the caches, and modify the physical memory protection and change the execution modes. From an SoC IP perspective, there are peripheral APIs for accessing common things like GPIOs, UARTs, timers, SPIs, plus many more. And like I mentioned earlier, we're adding more all the time with each release. Writing your software based on these APIs means that they can then be plugged into different frameworks or be used in standalone, portable bare metal applications. So looking closer, if we navigated into the Freedom Metal directory, there are a few folders to note here. First is the gloss folder. This has the retargeted syscalls as well as crto.s. Then there is the source directory, and this has all the implementations for the CPU and peripheral drivers as well as entry.s. Probably the most important directory here is the metal directory, and this has the header files with the function prototypes that you would want to write your portable applications against. This is also what the bulk of the documentation is written for. Great. Now that we have such a comprehensive understanding of what the Freedom E SDK is, I'd like to leave you with a few tips and tricks before we start the demo. The programming environment for the Freedom E SDK is a standard C programming environment. If you have some special code that you would like to be called before main, you can use the attribute constructor to instruct the build and execution to invoke that method as part of initialization. That is, it's called before main. While the overwhelming majority of embedded software is written in C, we have had a lot of requests to extend the Freedom E SDK to support a C++ environment. That's something you might want to look forward to in the future. Next is related to squeezing all the performance you can out of a function or method. By using the decorator, metal, place, and item, you can have code placed in memory that is as close to the CPU as possible, giving you the best performance. It's worth noting there is a call out about this in the documentation regarding inline and high optimization settings. So if you try this and it doesn't yield the expected results, have a look there. Okay, one last tip, and I think we might cover this in the demo later, but if you like the Freedom E SDK make-based command line workflow, you can create your own starting point and invoke all the same commands you just learned on your own program. In a terminal, using a copy command, recursively copy the folder empty and give it a new name in the software directory, my program in this case. That is the first command. Next, using a text editor or stream editor, search and replace the text string empty with the name of your new program directory, my program. You just did this in the step before. Finally, if you say make software program equals your new program name, in this case, my program, you're up and running in 2 easy steps with your own workspace. Okay, that's enough of me. Thanks for your attention thus far. I hope you found this enlightening and quite intuitive. If not, send me some feedback. Now, let's get to the fun part, the demo. Bunaroth, over to you.
Hello, and welcome to this demo part of the webinar. I am Bunaroth Su. I am a software manager and lead for the Embedded Runtime Software Group. I am going to walk you through how to build and run a couple of embedded RISC-V software examples using SiFive Freedom E SDK from the command line. I am going to do this on my Mac running High Sierra OS, but it also works on the Sierra OS. You can also use a Linux machine with Ubuntu 16.04 or 18.04. You can also use it on a Windows machine running Windows 10, but you will need to install the Windows subsystem Linux in order to run the command line. I will show you how to flash an FPGA RT bitstream for your design by using an open source utility called XE3S Pro. Once we flash the bitstream. I will show you how to easily upload the executables that we compiled from the software example onto the FPGA board and then run the program. The example that we are going to start with is a price zone benchmark program. We will compile and run it on the FPGA board to see the core performance number. To finish off, I will walk you through how to create your own software program using Freedom Metal library and build it and then debug it on the FPGA board. Before we can get started, we need to set up our environment with a number of RISC-V development tools. To make it easy for our customers and users, SiFive has pre-built packages available at our SiFive.com website. These packages are built from our GitHub repository called Freedom Tools, which is public. So let's get started. What I will do is to create a directory called webinar from my home projects, my SDK. Next, I am creating two more directories called SDK Tools and Demos. The SDK tool is where I will keep all the necessary development tools, while the demo is where I will keep the design delivery tar file that I downloaded from SiFive Core Designer. So, in case you have not been to our SiFive Core Designer webpage from SiFive.com, as you can see here on my left-hand side of the screen, you can simply just log in. And you can design a new core, or in my case, I will simply just download an E76 multi-core. And to do that, simply click on this particular button. Okay, what I have done is download two designs, one for the E76 and the other one for an E76 multi-core. And I have moved the download delivery tar file into our demos directory already, as you can see. What I also have done is create two more directories, calling it E76 and E76MC respectively. And I will show you the reason why I am doing that. Okay, the reason I create these two extra directories is because these delivery tar file all has the same format. Namely, the first level directory has a common name called SiFive_core IP, as you can see here. All right, as you can see here. Now, if I were to show you the same thing for the multi-core, and as a result, if I were to simply just untar this, one would override the other one. So instead of doing that, what we can do is simply by tarring it and stripping off the first level directory and place it into our appropriate directory. Similarly, we can do the same thing for the multi-core. Let me clear this slightly. All right, let's see what we have in our untar directory. Similarly, for the multi-core one, as you can see, if we were to simply just untie it, the last one would simply override the very first one. Okay, let's see what's inside each one of these IP delivery tar file after we actually untie it. Let's simply just go into an E76 multi-core. As you can see, what's in here is that we have the MCS or the bit stream for the FPGA. We also have the user guide and the manual for our core. And we have the software, which is under Freedom E SDK. In addition, the tar file will also have the RTL for you to run simulation using either Bravado, Synopsys VCS, or Cadence Exilium. Now that we have our design file with our bitstream and Freedom E SDK already, let's now download the RISC-V toolchain. Oops, that would be one too many. All right, let's clear some. All right, now that we have our design files and bitstream, it's time now to download the RISC-V toolchain. Let's go back to our webinar directory, and then we go into our SDK tools. So as mentioned early on, is that our pre-built toolchain are also available at our website by simply just go to sifive.com. At the bottom, you can click on board and software, and halfway through is where our toolchain. Now, to simply download, you can click and download the toolchain specifically for your machine, or in this case, I am going to basically grab them using wget. While I'm here, I will also grab the OpenOCD as well. So the OpenOCD is a GDB debugger server that allows you to connect to your end target. In our case, it will be the FPGA RT board. Okay, that one's done. Oops, wrong screen. All right. Now, one other tool that I mentioned earlier, which is the XE3S Pro. And that is actually available at our Freedom Tools repository. We have a pre-built release package that available here. And as you can see, you can also grab the other pre-built, like the toolchain, the OpenOCD, or the QEMU from here as well. So let me grab that. All right, now that we download all of our tools and utility, what I like to do is keep my SDK tool directory nice and clean. So what I will do is basically create another directory called download. And I will simply just move these tar file into my downloads. And the reason I'm doing this is that eventually after I untar these tools and utility, we need to set it into our path. And we can easily do this by simply omit the OS name from it, as what I'm about to do now. So I will create one for my OpenOCD. I will create another one for my RISC-V toolchain. Similarly, I will create another one for my XE3S Pro. And once I've done that, just like we did last time, is that I will untar this tar file. Into its appropriate directory. Okay, let me clear this. And similarly for the RISC-V toolchain. And lastly, for the XE3S Pro. All right, let's see what we have. Okay, we basically have all of our toolchains and utility untar. Let's start setting up our environment. All right, let's see if the environment, if our tools are actually in our path. Okay, we have one for make. And we have a GCC. Similarly for our flashing utility. And we are set to go. Okay, now that we have everything, let's go into E76 MC directory that we untied earlier. And in order to build the program, let's go into the Freedom E SDK. And one thing I would recommend you to do is do an ls of the BSP directory. And as you can see here, there are two targets that we can build a program for. One is for the RT board, and the other one is for an RTL build. In our case, we will be using the design RT for our FPGA RT board. And to build a program, in our case, the dry stone, we can do that by simply type make program, the name of your program that you want, and then specify what target you need to build this for. In our case, it's a design RT, and simply just say software. And as you can see there, it first built the Freedom Metal library. Once that's done, we will build the Drystone program. And as you can see, at the end, we do have a hex file or an ELF file that we choose. And as you can see here, this is the size and the data of our program. What I also like to show you, there are a number of different examples included in the IP delivery. So if you actually do ls software, as you can see here, these are a number of examples or sample software that you can actually build and run on your particular target. However, in order for us to load our executable onto the FPGA, we first need to connect our board to our computer. Okay, before we can load and run the executable that we just compiled, you will need the following to connect to your host machine. The first being an RT-A7 board, which is made by Digilent and available from DigiKey, as shown here. I would recommend you grab the 100T type one, as it has a larger FPGA footprint. You will also need two types of USB cable. The first being a type A to a micro B, where the micro B is connected here. This is for powering the board as well as providing console output. The other USB cable, which is a type A to a type B, where the type B will be used to connect to the tiny debugger module. You will also need 10 male to female cable for connecting from the tiny debugger module to the female PMOD here. For SiFive customer, SiFive does provide these male PMOD connector, as shown here. All right, let's connect this up and power up the board. Okay, as you can see, that's very nice and bright. For a more detailed information, you can also go to sifive.com. At the bottom, under documentation, you can take a look at this core IP FPGA evaluation kit user guide. And in it, it has all the information required for the hardware, as well as how to set up the board. Okay, now that we have connected a RT board to a host machine and power up already, let's see if our host machine can actually detect the RT board. And you can do this by running an ls USB command. And as you can see, it is available here. And next, we want to flash our FPGA board. And remember early on was that our bit our bitstream is actually located here under this directory here. So if I do this, there's our bit file. And as mentioned earlier, we will be using an open source utility called XE3S Pro utility instead of the Xilinx Vivado. So let's find out one more time if our utility is actually in our path. It is. So to flash the bitstream, simply type in the utility name with the argument -c, next CS4, and the location of the bitstream. In our case, it is design.bit. Let's take a couple of moments. There you go. It is done. All right. Now that we have flashed our FPGA bitstream, we need another console terminal for our console printout. But before we can do that, let's find out which particular USB serial that we should be connecting to. Okay. And what I'm going to do is I'm going to use screen to connect to our console. And I will use the second one with a baud rate of 1115-200. Now that's up and running. Upload our executable. And as you can see, just like when we make the actual program, we can basically use an upload command at the end. And now, as you see on the left-hand side, our Drystone executable, which we compiled previously, is being run. This will take some time. All right, it's done. Now let's calculate the Drystone score, which is DMIPS per megahertz. And you can do that by using a calculator. So I'm taking the Drystone per second divided by the Vex constant, then divide by the frequency of this board, which is 32.5 megahertz. And so the Drystone score for E76 multi-core is slightly below the advertised number, but that is because we are actually running this from the flash, whereas on a single core, we would run this from a much faster memory, which is an item. All right, just to show how easy it is to use Freedom E SDK to build and upload the same program across two different designs. Remember, I actually have another design called E76 here. Okay, I'm simply going to CD into that. And while I'm there, I can basically reflash my FPGA. It's the same FPGA board, but this one, it's a different bitstream. And this time it for an E76, not for the E76 multi-core one. The E76 is a single core. Let's try again. Upload our program. Okay. Now this time, because it is a single core with an item, we should see better Drystone score. All right, it finished. Let's see, the number is actually better. And as you can see there, the score should roughly the same as what is being advertised for RE2600. So next, I'd like to show you how to create your own C program. There are many different ways to do this. You could start from scratch by first creating a directory under software, then a makefile, and then your own program header and source file. But the easiest way to do this is to simply copy the empty program in which its purpose is to serve as a template for creating a new program. So from the Freedom E SDK, where we typically build all the program, we can do copy from software empty to software demo, where demo is a new program. Haven't done that, simply modify the makefile. Where we change the program to demo. Next, we want to actually edit our main. Okay, just to make things much faster, what I will do is I copy a sample that I already written. All right, there it is. Okay, so what this program does is simply do some printing. And as you can see, what Freedom Metal API provide is that you can still use the standard library function like printf, but also specifically to Metal API itself. Metal API provide an API where you simply can pass in a label to get a handle for an LED in this case. And then, as you can see here, what I'm doing is simply just put a loop where we can simply toggle the LED. In addition, what I also do is basically have a simple wait function based on the number of cycles that you want to wait. And as you can see, this wait function is up here. What it does, it's simply just retrieving the M cycle count from the core. So in this case, I'm simply grabbing the value at the start and then keep grabbing the new count until the count is actually sort of greater than the start value plus a wait time. Okay, so with that, we can basically save it. Let's see if we can compile it. So instead of dry stone, we can simply just change it and compile it and upload at the same time. Okay, so that's it. Yeah. I guess in this particular case, the wait time must be very short. We can actually sort of go back and modify that. And let's say this time we increase by a factor of 100. Make it 1000, see what happens. Again. Oh, it's still very fast. Okay. Next, I'm basically want to show you how you can go about debugging as well. So simply just replace the upload command with a debug. So what that will do is simply load the program and then launch the GDB. And then from here, you can do a load. And then let's say we break it main. Okay. Okay. We set a breakpoint on main. We then continue, and now it break. When we enter main, we can also do a list, a regular GDB debugging operation. And as you can see, currently it's at it's about to execute line 23. We can do a step, right? And as you can see, it printed out. Can step. Okay, so the next line that it's going to do is actually call the enable LED. We can even step into that. Okay, so we step into the function. As you can see, that's nothing more than a thin wrapper that the Metal API provide. And I can step again, which actually take us down to the actual driver, the LED itself. Here you can step through. You can finish it off, finish the particular function, right? And then finish our wrapper function as well, which now bring you back into main. So it's the normal regular GDB debugging. Then you can also basically do a watch point on, let's say, in my case, I just say watch on I. We can basically run continue and see what happened. Okay, so there must be a change, right? So I can go again. So every time the I value change, the watch point on a particular variable break for us. Okay, and now it's 2. That means we should be able to simply step out of that. Yep, and we exit from the for loop and about to return from main. So as you can see, Freedom E SDK provide a very simple command line environment that you can create your own program as well as build and compile some of the existing demo for you to try it out as well. And it make it much easier for you to upload onto your target, in this case an FPGA RT, as well as launch into a GDB debug session. So thank you. Back to you, Bernard.
Okay, thank you, Gunaroth. Sorry, we're out of time for a Q&A. So please submit your questions and SiFive will respond to you via email. I do also want to remind you about the next upcoming webinar. SiFive will introduce their HBM2/E IP subsystem with features and implementation guidelines. Thank you for your attendance.